So let's take a look at resonance and drawing resonance structures in organic chemistry. So a little bit more than 100 years ago, the structure for benzene was first proposed, with alternating double and single bonds between carbons in a six-membered aromatic ring. Of course, as a line angle formula, we'd normally draw this without the hydrogens and leave out the chemical symbol for the carbons. So these double bonds proposed in benzene suggested that it would have chemistry like an alkene. Alkenes are a hydrocarbon molecule with carbon-to-carbon double bond functionality. And we expect to see very particular kinds of reactivity from alkenes, things like addition reactions, where a molecule like bromine can add across the double bond and we produce a dibromoalkane. However, benzene does not react with bromine to produce this brominated alkane molecule. So without the same kind of chemistry, people questioned and argued whether benzene had this kind of double and single bond character. Furthermore, when we looked at the chemical bond length in a benzene ring, it was found that the carbon-to-carbon bond length was exactly the same for all 6 of the carbon-to-carbon bonds. Now that doesn't make sense either initially, because a carbon-to-carbon single bond is longer at 154 picometers than a carbon-to-carbon double bond, which is only 134 picometers. So how could the bond length at 140 be exactly the same all the way around the benzene ring? Well, if we look at the alkenes for a second and think about how that double bond, the pi bond, is formed, of course we've got sp2 hybridization for each of the carbon atoms in the double bond, the hybrid orbitals in blue there, spread out trigonoplanar around the carbon, and then that last unhybridized atomic p orbital stretches up and down above and below the ring. Likewise on the second carbon, and so it's this perpendicular overlap of these atomic orbitals stretching around the original sigma bond that creates that second bond, the pi bond as it's known. Now to get efficient overlap, the two carbon atoms have to be drawn closer together. That explains why the carbon-to-carbon double bond is shorter. We need greater overlap. So when we think about that benzene ring with 6 sp2 hybridized carbon atoms, again the atomic orbitals have to overlap to make the pi bond. But each atomic orbital isn't just overlapping with its neighbor on the left, it's also overlapping with its neighbor on the right. So we've got a continuous set of overlapping atomic orbitals all the way around the carbon ring. So those electrons in the pi bonds are no longer localized between two carbon atoms, they're actually delocalized around the entire carbon ring. And this is what creates a ring current around the benzene ring. So we normally draw the benzene ring with this donut-like structure of electron density above and below the ring, representing those 6 overlapping atomic p orbitals. So this ring current of delocalized electrons explains why each carbon-to-carbon bond can be the exact same length, and explains why the nature of benzene is unlike the nature of alkenes, because alkene bonds are localized, they're not delocalized. And it can explain therefore why we would see some changes in the chemical reactivity. And this ring current exposes the limitations of drawing Lewis structures. One single Lewis structure cannot properly draw and show the nature of the benzene ring. It was Pauling who first suggested the idea of resonance structures, multiple Lewis structures, and we see the overall nature of a molecule by looking at all of these resonance structures together. So for example, with benzene, a single line angle formula cannot show the true nature of benzene because we're implying single bonds and double bonds. But we can show through resonance structures, as the atomic orbitals line up and overlap with each other, how that ring current would happen. And I'll just get rid of these for a second. And so the electrons are delocalized, and the electrons can move to the next two carbons, which forces the next pi bond to move, and then the third pi bond to move. And we end up with a new resonance structure with the double and single bonds in the alternative positions. So looking at the two resonance structures together, we see that each carbon-to-carbon bond has a mixture of double bond and single bond character. And each of them the same explains why we get this ring current and why the bond length is exactly the same. So a couple of general rules to think about in addition to what we talked about in class. So for when we're drawing these resonance structures, we're not going to alter the basic skeleton of the molecule. The original sigma bonds between each pair of atoms will always remain intact. The only thing that's going to change as we move from one resonance structure to another is the lone pairs and the pi bonds. So the only changes we should see are lone pairs becoming pi bonds and pi bonds being turned into lone pairs. That covers most of the general rules. So let's look at some examples and apply these general ideas. So if we look at nitrite, which is one of the polyatomic ions that you would have seen in Chemistry 151, it's a molecule which is capable of resonance. Now the easiest way to get your N, or your starting point for the resonance in a molecule, is to look for the atom with the electrical charge. Electrical charge is a point of instability in the molecule. The atom doesn't like being charged, and when it's negatively charged, it would like to offload electrons because it has too many for its share. So here's our starting point, and we're going to try and offload electrons from the oxygen. So we can show an arrow which shows where the electrons come from and where the electrons are going. The electrons, instead of a lone pair, are going to become a bonding pair, which is going to reduce the electron density around the oxygen. Now of course the nitrogen next door, which is going to receive these electrons and share them to make the pi bond, it already has an octet, 2, 4, 6, and a lone pair, 8 electrons. And nitrogen cannot break the octet rule. So as the electrons come in, the existing electrons in this vulnerable pi bond have to retreat back to the oxygen atom on the end. Again, we show this resonance arrow, this mechanism arrow. This is where the electrons begin, and the electrons are going to be farmed out to the oxygen as the electrons in the bond retreat back. And we can now show that new resonance structure as the mechanism arrows suggest. That lone pair has turned into a pi bond, so now the oxygen only has 2 lone pairs, and that pi bond has turned into a lone pair, so now this oxygen has 3 lone pairs instead of 2. That's a common trait as we move from one resonance structure to another. The number of pi bonds in each structure and the number of lone pairs collectively, 1, 2, 3, 4, 5, 6, should be equal to every other resonance structure, 1, 2, 3, 4, 5, 6. So the number of pi bonds and the number of lone pairs usually matches for each structure. And one aspect of these resonance structures, which can't be shown from a single structure, is that each of the bonds has partial double bond character. And it explains why the bonds in nitrogen to oxygen for the nitrite are the exact same length. If we look at just one of the structures, that would imply single and double bonds, which would be a different length from each other. Double bonds are always shorter than single bonds. Let's look at another example, this time carbonate. Another polyatomic ion that you should be familiar with from Chemistry 151. So we'll look at that initial structure. We've got a carbon at the center and one double bond and two single bonds. Again, showing us the limitations of Lewis structures because we can't break the octet rule for carbon. So our starting point as we try and draw additional resonance structures would be one of the two atoms with a negative charge. The charge is destabilizing. It's a hot potato and the oxygen would like to offload that electron density, and it will do that by turning a lone pair into a bonding pair, a pi bond between the oxygen and its neighboring carbon. Remember, every time the electrons move, they're only going to move to an adjacent atom. There's nothing more drastic in where the electrons go. So as those electrons come in, swing in to make a new bond, remember the carbon already has an octet, 2, 4, 6, 8 electrons, and it cannot break the octet rule. So as the electrons come in, something has to give, and it's the existing pi bond between the carbon and the oxygen. So those electrons swing out and retreat away from the carbon to allow room for the incoming pi bond. And so we show this resonance structure for the carbonate where this lone pair has become a pi bond and that pi bond has become a lone pair. We've got the same number of pi bonds and the same number of lone pairs in our second resonance structure. And when we're dealing with a negative charge, we often see this kind of symbiotic relationship as we move from one resonance structure to the next. For every lone pair becoming a pi bond, there's normally a pi bond becoming a lone pair. So now with our second structure, we can take it a step further because we've got this negative charge on the oxygen here, which hasn't seen any relief yet. So we imagine a lone pair of electrons being offloaded to the carbon to make a carbon to oxygen double bond. And of course, because there's an octet on the carbon, that has to give, and so these pi electrons retreat and swing back to maintain the octet, and we produce our third and final resonance structure, each one with one pi bond and the same number of lone pairs of electrons, 8 lone pairs and one pi bond each time. So the resonance structures combined again show the true aspect of the molecule, which would be camouflaged and hidden if we look at just one resonance structure. And no surprises, each of the carbon to oxygen bonds in carbonate is the exact same length. Looking at one of the three structures would suggest that one of the bonds, the double bond, is actually shorter than the others. But they are all the same length, and we get a clue to that by looking at all three resonance structures. Let's try another. This time look at a more organic molecule. And this time we've got a molecule with a positive charge. That positive charge in the carbon will almost always imply that we've got a carbon with an incomplete octet. And it's a carbon which is less stable. It would like to have an octet. It would like to become stable. And notice in these molecules that we're going to draw, we've got a continuous chain of carbons which are sp2 hybridized with atomic orbitals above and below the plane. Let's highlight that for a second. So the carbon here on the end, it's got an empty atomic orbital, hence the positive charge, and then the other carbon atoms have atomic orbitals which are being used with a neighboring carbon's atomic orbital to make that pi bond. But with this continuous sequence all through the line, we don't have localized electrons in these bonds, we've got delocalized electrons around the molecule. The last two carbon atoms, of course, sp3 hybridized because there's two hidden carbon to hydrogen bonds. So let's show some resonance. We'll get rid of the atomic orbitals and start to show how the electrons flow. So here's a weak spot. It's a carbon which doesn't have enough electrons, so it has to draw electrons from a carbon neighbour. Again, it doesn't have too many, it's got too few because of that positive charge. So the pi electrons next door can swing around in the overlapping atomic orbitals and move the electrons to that carbon atom and come to its rescue. Now if we look at the resonance structure produced when this happens, the octet has been completed as these electrons swing round, pivoting at a gate like a gate from the near carbon position, swinging around, plugging in the gap, and the far end carbon loses its octet because it no longer has access to those pi electrons. So we've moved the charge on, we've moved the problem around the molecule, and this is now the new weak position in the molecule. This is now the carbon which is desperately crying out for extra electron density, and it looks to its neighbour with pi electrons, so we can swing that bond around to plug in the gap and produce a third and final resonance structure, shifting the electrons around, and so the charge hops around to the end carbon, which no longer has access to the pi electrons and is now the positively charged carbon. These resonance structures help to show how this structure is more stable because through resonance we move that positive charge around. It's like trying to move from one apartment to another. The more friends you have to share the burden, the more stable and the easier the job becomes. So with other atoms, to move that positive charge to as the electrons flow between the atomic orbitals, it makes the molecule more stable. More resonance structures means greater stability. Let's look at one more before we stop. This time back to a negative charge again. That's a hot potato in the molecule. And a negative charge means that the carbon has too many electrons. Okay. Again, we can look at the extended system of atomic orbitals above and below the plane. And we can see that the carbon atom with the charge actually has a lone pair in the atomic orbital, while the rest in the sequence are using those atomic orbitals to share pi electrons. But remember, they're not really localized pi electrons in double bonds, they're delocalized electrons around this entire atomic orbital sequence. So let's get rid of the atomic orbitals, we'll assume they're there. And let's look at how the electrons flow. So there's too many electrons and we have to unload them to a neighbouring carbon by turning the lone pair into a pi bond. That carbon next door, of course, already has an octet. There's one carbon to hydrogen bond which is not being shown. So as a bond comes in, a pi bond, the existing pi bond has to retreat and move out back to the far away carbon. So we can now show our first or second resonance structure with these arrows and show that the lone pair of electrons has hopped 2 carbons down the line, because that lone pair becomes a pi bond and the pi bond becomes a lone pair. So this is now the weak spot, the instability spot in the molecule. So we're going to show electrons moving from this position, offloading electrons to the neighbouring carbon to make a new pi bond, and with the neighbouring carbon already having an octet, it has to offload its existing pi bond and move them back to the far end of the bond. We're now ready to show the resultant new resonance structure. Remember, same number of pi bonds, same number of lone pairs each time. Now this is our new weak spot, the new spot of instability in the molecule. So we can show that lone pair of electrons being offloaded to the neighbouring carbon. Of course, the neighbouring carbon has an octet, so it has to offload the pi bond which it's attached to and send those electrons back to the far end of the bond, and we can now show that remaining resonance structure. More resonance structures, more stability for the molecule. And don't forget your resonance arrows each time. We show where the electrons are coming from the lone pair, and we show where the electrons are going to, between the two carbons to make the pi bond. We show where the electrons are coming from, the pi bond, and we show where the electrons are going to the carbon to form a lone pair. Look out for another video later this week with some extra examples to challenge us.